Colligative properties are basically features that can be analyzed from the perspective of the types of solutes that are dissolved into solution. So basically, a solvent will have a specific boiling point or vapor pressure or freezing point associated with it. But when you add a solute into the solvent, you create a solution, and you subsequently change that freezing point or that boiling point. Depending on the type of solute that you add. So basically, the four types that will be looked at in terms of colligative properties will be vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. In this video, we're going to focus on the boiling point elevation and the freezing point depression specifically. And in a follow-up video, we'll be looking at vapor pressure lowering and osmotic pressure. So remember, colligative properties don't depend on the identity of the substance being dissolved in so much as it depends on the concentration and the particles that are actually floating around in that solution. So from the perspective of freezing point depression, basically the freezing point of a solution is going to be lower than the freezing point of just a pure solvent by itself. So that's why we salt our roads during the winter time in areas where it's snowy or icy. And in that same way, boiling point elevation occurs when you add a solute into a solvent and create a solution. So we're going to be looking at freezing point depression and its specifics, as well as boiling point elevation, how to do calculations with it, and basically the appropriate approach for different types of solutes. So the equation that we utilize in order to figure out how much of a change is going to occur is the one that we see right here. Okay, so this delta T represents the change in temperature. It does not represent the new boiling point or the new freezing point. It just represents the amount of change that's going to occur. K is a constant, and it's based on the solvent that's being used. So you're going to either look this value up or it's going to be given to you in the problem. M is your molality. And recall that molality is the moles of your solute divided by the kilograms of your solvent. And you would do that calculation to get your M value. And I is actually something that's new to some of you. So I is your von Hoff factor. Basically, that's the number of particles. And the von Hoff factor is going to be dictated by the type of solute that you have. So whether you have a covalent or an ionic compound, how many particles it breaks into in solution, etc. And we'll discuss how to figure out the value for your von Hoff factor in a moment. What I want each of you, though, to recall is that this delta T that you have right here is not telling you the new temperature. It is just telling you the change in temperature that's going to occur. So please make sure that you're paying attention to that, because a lot of people make that mistake. So let's go ahead and let's look at how we're going to figure out the number of particles associated with the I value, or your von Hoff factor. Okay, so when you're dealing with non-electrolytes, okay, so guys, recall, non-electrolytes are things that do not break into solution, or sorry, into ions when they're added to solutions. So, and these types of compounds, these non-electrolytes, are going to be covalent compounds. So something like sugar, things of that sort, boron, trifluoride, etc. Okay, so covalent compounds are going to be non-electrolytes. They remain intact when you put them into water. So what does that mean? That means that there's only a single particle. So if I take a sugar molecule and drop it into water, there will still only be one particle. Okay, and so whenever we're figuring out von Hoff factor, we're going to look at the type of compound. If it's covalent, okay, we know that our von Hoff factor is going to be 1. So I is going to be equal to 1 because there's only one particle being put into solution. Now, this becomes a little bit more detailed when we start to talk about the von Hoff factor with respect to electrolytes. Okay, so when we talk about ionic compounds, so compounds that break into ions when you're dissolving them. So something like NaCl, right? We've previously seen that NaCl breaks into sodium ion and the chloride ion. Okay, so if I
have both of these, notice that the NaCl breaks into 1, 2 ions. Okay, so my von Hoff factor for NaCl would be 2. Okay, same thing for barium chloride. Okay, we're going to have 1 barium ion and 2 chloride ions, so that's going to give us a von Hoff factor of 3. Sodium nitrate, we have a sodium ion and a nitrate ion. Okay, those are 2 ions, so our von Hoff factor will be 2. Okay, so hopefully you guys see that the von Hoff factor for electrolytes, which are going to be ionic compounds, are going to correspond to the number of ions that each molecule puts into solution. Okay, if we're dealing with covalent compounds, the von Hoff factor will always be 1. It's always going to be an I value equal to 1. Okay, so let's look at some practice problems. So they ask you to find the freezing point of a saturated solution of NaCl containing 28 grams of NaCl in 100 milliliters of water. Okay, so how are we going to go about doing this? Okay, so my suggestion to you is to first and foremost write out the equation that you're going to be utilizing. So we're asking about freezing point. There is a solution being created, so we know that this is going to be a colligative property calculation. So we know delta T is going to be being utilized. Okay. Now, the next thing we can look at is we can look at the various pieces. So delta T, obviously, we don't know what that is. Okay, we haven't been given that, so we have no idea. Okay, K, we've been given that here. This is our freezing point constant, so 1.86. Okay, and then our I value. Notice we have NaCl. NaCl is an ionic compound. NaCl breaks into Na plus Cl minus. This is balanced, so my I value here is equal to 2. So, okay, so far I have my K, my I. Now let's look at M. Okay, so remember mole, excuse me, molality is going to be the number of moles of solute divided by kilograms of solvent. Okay, now moles of solute, we don't have that. We have grams of solute, right? So we're going to have to take 28 grams of NaCl. Okay, we're going to divide by our molar mass, which we've been given here. Okay, and this is going to give us 0.48 moles. Okay, so I have 0.48 moles of my solute. Okay, now I need to have kilograms of solvent. Okay, now my solvent in this case is water. I have 100 milliliters of water. I know that the density of water is basically 1 gram per milliliter. So if I have 100 milliliters, I'm going to have 1 gram per 1 milliliter. Right, so 100 grams of H2O is what I have. Now if I convert that to kilograms, that means I'm going to have 0.100 kilograms. I just moved that decimal point. Okay, so 0.100 kilograms is what I'm going to have here. Okay, now when I go ahead and do the math here, my quick division, I'm going to get a molality value of 4.8 molal. Okay, so look, I have K, I have I have M, so this allows me to calculate for delta T. Now remember guys, delta T represents the change in temperature. Okay, so the actual physical change, the number of degrees that freezing point is going to be altered. However, what I want you guys to also pay attention to is the fact that they didn't ask for the change, they asked for the new freezing point of the solution. Okay, so that's going to require an extra step after we've used this equation, and we'll look at that here. So delta T is going to be equal to 1.86 times our 4.8 molal times our von Hoff factor, which is 2. So 1.86 times 4.8 times 2, that's going to give us 18 degrees C. Okay, So remember, molality is moles per kilogram. So moles and kilograms are going to cancel here. Degrees C is left over. So this is what our change in our freezing point is going to be. Now, that is with respect to just water. Okay, so my solution is not just pure water, it's solvent and solute combined. So in this case, NaCl dissolved into water. So what I'm going to do is, in order to find the new freezing point of the solution, I'm going to take the freezing point of the solvent, which in this case is 0 degrees C, because water's freezing point is 0. Okay, and then I'm going to subtract my 18 degrees C. So the freezing point of my NaCl solution is going to be negative 18 degrees C. Okay, and this makes sense, guys, on a lot of levels. So basically, if you think about the reason why they salt roads, or when you're making ice cream, things of that sort. So basically, we salt roads in order to make it where the ice doesn't form. So basically, ice would just form if there was just water on the road and it got really, really cold in the evening. So below freezing. We add salts to the road in order to basically lower the freezing point of water. So basically we create a solution that then makes it where the temperatures have to get even lower in order for ice to form. Okay, so we would expect a lower freezing point, hence a freezing point depression. So let's go ahead and let's look at another example. At what temperature will a solution that is composed of 0.73 moles of glucose and 225 grams of phenol boil? The boiling constant is 3.60 degrees C kilogram per mole. Okay, so once again, we're being given a solution. They're asking us about basically a new boiling point. Okay, so we know that we're going to be utilizing this equation. So just like we've done in previous examples, okay, so delta T, we do not know this. This is one of the things we're solving for. Okay, K, we've been given. Notice that this is the boiling point constant associated with the solvent. Okay, so guys, in this case, our solvent is our phenol, right? Because that's what is the solvent for the solution, or for the solution that's been created. Okay, our M value, remember we're going to have to calculate that. Okay, so we've been given our moles of solute, and we've been given our number of grams of solvent. So what we're going to do is just convert those into the appropriate thing. So 0.73 divided by 0.225 kilograms. Sorry, and this should be moles. Okay, so we're going to go ahead and calculate that. That's going to give us 3.2 molal. Okay, our I value. Okay, so remember, glucose in this case is our solute. Glucose is a sugar, so carbon, hydrogen, and oxygen molecule. So that's going to give us a covalent molecule. Remember, our I value, our von Hoff factor, is always 1 for covalent molecules. Okay, so now we have all the components in order to calculate delta T. So delta T is going to equal 3.60 times 3.2 molal times 1. Okay, we go ahead and multiply all of those out, and those are going to give us 12 degrees C, right? Kilograms and moles, those are going to cancel with molality. Degrees C is what's left. So our change in temperature with respect to our solvent is going to be 12 degrees C. Okay, so our boiling point elevation is going to be 12 degrees higher than what our solvent would normally boil at. So phenol, which is our solvent, normally boils at 181.1 degrees C. Okay, so in this case, because it's a boiling point elevation, we're going to add our change in temperature, right, because it's a boiling point elevation. Okay, we're going to add our delta T to this. Okay, and this is going to give us 194 degrees C. So this would be the boiling point of our glucose and phenol solution. So once again, we're utilizing the delta T equals KMI calculation. Notice that's not where I stop in this situation. This question is asking me at what temperature the new solution is going to boil. So delta T tells me the change that's going to occur, but I need to take this extra step here in order to figure out the new boiling point of the solution. And all you do is you figure out what the solvent's original boiling point is, and you subsequently add the change in temperature that's expected to occur based on the equation here. So these are the basics of colligative properties for boiling point elevation and freezing point depression.